Greetings and welcome back. Today we're going to be looking at the way that molecules form in three-dimensional space. So moving away from Lewis structures where we just see them all laid out flat on a paper to thinking about how they actually form in space. The reasons for this, and this is the big picture for all of today, is that electrons like to pair up, and in general electrons like to also spread out. So pairs of electrons which are negatively charged don't like to occupy the same space as other pairs of electrons that are negatively charged. So besides two electrons wanting to pair together, in general electrons want to spread out as far as they can in three-dimensional space. So we're going to begin by looking at the simplest atomic orbital, which is 1s. And so the very first orbital, which would have one electron, would be the 1s orbital. This is the lowest energy orbital, and this corresponds to hydrogen with one electron. Something like that. All right, so what we can tell with this is that the nucleus of hydrogen right here has one proton, and then there's a cloud in which an electron is generally floating around it. And so this is a 1s orbital. It's shaped like a sphere. We populate it with one electron. All right, so if two hydrogens get together, in general what happens is we move from this atomic orbital, which is the orbital associated with just an atom, to a molecular orbital, which is the new molecule's orbitals. Molecular. So when we have two hydrogens get together, we basically take two different 1s orbitals, each of which has a nucleus and an electron floating around it. And we make something brand new. And what happens is that these two electrons essentially share space in between those two nuclei. So we would draw this in terms of Lewis structures as just H-H, which essentially is just telling us that the electron pair, right, a bond is two electrons, tends to spend its time in between the two hydrogen nuclei. When electrons generally share that area in between the two nuclei, we call that a sigma bond. All single bonds are sigma bonds. So this is what we would always find when we have a single bond, is that electrons would therefore be shared in between the two nuclei, and that this positively charged nucleus and this positively charged nucleus would share a pair of electrons in between. And that is how we go from atomic orbitals, which are 1s, to a molecular orbital, which would be a sigma bond. All right, so no matter what the molecule is, I'm going to draw out CH4, which is just methane. Anytime you see a single bond, it is a pair of electrons being shared between the nucleus of hydrogen and the nucleus of carbon, or in this case, the nucleus of hydrogen and the nucleus of hydrogen. Well, if we consider methane, we will have a problem. So let's go backwards to the atomic orbitals for carbon. So carbon is 1s2, 2s2, 2p2. So if you look at the periodic table, it has six total electrons. These are in the core, the 1s2, and all of these guys are in the valence shell. So essentially, if we line this up the same way that we did for hydrogen, we would have a 1s orbital with two electrons, and then we would have a 2s orbital that had two electrons. And then, if you recall, we have three 2p orbitals, and we would have two electrons total in that. And that's where we would get our four valence electrons from. You may recall from general chemistry that in three-dimensional space, while an s orbital is just centered around the nucleus, the p orbitals exist as three separate propeller-shaped guys, which exist in an x, y, and z direction. So this would all be nice and flat, but I'm going to draw another one which would be essentially coming out at you and going kind of back behind that thing. So if you consider that this thing, which is just our carbon atomic orbitals, we have one s sphere in the middle, we have three of these p orbitals, they would need to spread out as much as they could in three-dimensional space to reach out to four hydrogens in order to form methane. it cannot happen with atomic orbitals the way that they exist in carbon, or indeed in nitrogen or oxygen or anything else. So what happens in order for these four orbitals, the s and the three p's, to make four different sigma bonds in three-dimensional space is they have to hybridize. So we will move on and look at that in just a second. The way that hybrid orbitals form is hybridization of anything, is mixing different things together to make something new. So first off, what happens is that we have, in three-dimensional space, we're going to have a carbon nucleus, and we're going to have four different hydrogens, and all of them are going to want to make a bond to methane, or to carbon, in order to make methane. The problem is they want to spread out as far as they can in three-dimensional space. And the best way to spread out in three-dimensional space is not to make just flat lines on a plane. So instead, we end up with something tetrahedral, which means, if you recall, something that looks essentially like this. You get kind of what looks like a tripod with something sticking straight up. And that would be the best way for, remember the bonds, these four bonds, are just pairs of electrons. And what they're doing is spreading out as far apart from each other as possible, because regions of electron density, that is to say areas in which electrons are found, are always composed of electrons. And electrons are always negatively charged. Therefore, they want to spread out as far as they can in three-dimensional space. So the way that we describe this happening is that we are taking our S and our three P's, and we are going to put them through the hybridizer. We will just say that they hybridize. And what we get out are four orbitals, each of which are called sp3. So we took one S and three P's, we mixed them all together. Because we had four orbitals, we still get four orbitals, but each one of these is 25% S and 75% P, as you can tell, because it's 1 part S to 3 parts P. And so each of these look like that. And in three-dimensional space, we describe these guys as looking something like this. They have a little lobe and a big lobe. Because there are four of these, what happens is that the carbon nucleus, instead of looking like what we have above, where it has an S and three different P's, it would have simply four sp3s. We would have an sp3 that looks like this, sp3 that looks like this, an sp3 that's where the big lobe is coming out at you a little bit, and then an sp3 where that big lobe is going away from you. And that is essentially this. It is the tetrahedral shape that we see when we have anything that is hybridized as sp3. You'll also notice that we had four total electrons, 1, 2, 3, 4, in these atomic orbitals, and they like to spread out, so when we have places of, or orbitals of equal energy, we would have one electron in each. Therefore, we would have one electron in each of these. And remember that each electron likes to pair up, and the way that we make covalent bonds would be for a hydrogen, which remember, hydrogens are just in s orbitals, to approach the ends of each of these. These are just my hydrogens. And therefore, what we would get is a nice sigma bond in each of those locations in between the hybrid orbital, the sp3 coming off of the carbon, and the s orbital coming off of the hydrogen. And that is how we make most of our sigma bonds. They go in between either a hybrid orbital and an s, or in between a hybrid orbital and another hybrid orbital. But they're always between the nuclei of one atom and the nucleus of a different atom. So this is how we make sigma bonds. So if you are given a molecule like, let's say, water, we'll look at water. Water is just simply H2O, and the Lewis structure of it would look like this. Well, anytime you have electrons that are not making a double bond or a triple bond, so just electrons by themselves, here's one pair of electrons, here's another pair, and another pair. It doesn't matter whether they're in bonds or lone pairs. They want to spread out as far as they can in three-dimensional space. Therefore, this oxygen has 4 regions of electron density, and each of those guys would hybridize to an sp3. So really what oxygen looks like when it forms the water molecule is that you're going to have a bond to a hydrogen, another bond to a hydrogen, and then you'll have kind of a pair of electrons up here and a pair of electrons down there. And that's how they spread out in 3-dimensional space. What we have measured is that, in general, the average bond angle between the bonds in a tetrahedral or an sp3 carbon or oxygen or nitrogen or whatever is approximately 109.5 degrees. This is an odd number, literally and figuratively. I don't know. This is a very strange number to use, but this is what we find, is that 109.5 is roughly going to be the bond angles for any sp3 hybridized atom. Up until now, all we've been talking about is the formation of single bonds. And remember that a single bond is always a sigma bond. A sigma bond just describes electrons being shared in between 2 nuclei. So what happens when you form a double bond? All right, so let's draw a structure that has a double bond. And so we will use formaldehyde, which is a very simple molecule that forms a double bond. So going back to the very last thing we did, what we will see is that coming off of that carbon are only 3 regions of electron density, and therefore this carbon only needs to make bonds in 3 directions instead of 4. Yes, there is a double bond, but with a double bond, the electrons still need to be between the carbon and the oxygen. Therefore, this still counts as 1 region of electron density, and each of these bonds counts as another. So, this carbon doesn't need to make 4 bonds, it only needs to make 3 areas in which the electrons go. So, for this carbon, remember that we would have, again, a 2s and 3 different 2p's. Well, if some carbon, some atom, wants to only have its electrons spread out in 3 directions, what it needs to do is take an s and 2 p's and form 3 different orbitals, all of which are a mixture of 1s and 2 p's, therefore we call them sp2. And what we would have is one leftover p orbital that would be unhybridized because it didn't get in the mix. Right? Each of these sp2s would be 33% s because it's 1 part s, and 67% p because it's 2 parts p. The way that these p's would be spread out in 3-dimensional space looks something like this. We would have sp2s, and sp2s look a lot like sp3s. They're actually a little bit shorter because they're more s than an sp3. Remember, an sp3 was 25% s. Well, these are 33% s. And s, which is just that sphere around the nucleus, is much closer to the nucleus. Therefore, these guys are shorter than an sp3, and they make shorter bonds. So the way that they would spread out in 3-dimensional space would actually just be perfectly flat. If you want to spread 3 things out as far as you can, you would just spread them out like this. And each of these are sp2 orbitals. You would have a leftover p orbital, and that p orbital would go into that empty space. And as we look at this, the empty space, as you're facing this, is actually coming out at you from the carbon, and the other half of the p would be going away from you. So what I'm going to do is tip this guy up on its side. So I'm going to take one of my sp2s and just put it off to the right. Then I'm going to take one and say it's coming kind of out at us, but flat, and then one that's kind of going away there. So those are all planar. And these are, again, all your sp2s. But we have that one leftover p orbital, and that p orbital is going to be half up, half down. And that's your p orbital. Again, we have 1 p orbital and 3 sp2s. All of these are spreading as far out from each other as they can in 3-dimensional space, because once again, there's an electron in each of these. Remember, we have 4 valence electrons for carbon, and therefore we have 1 electron in each of these locations. And the p orbital has 1 electron shared between the top and the bottom. But this is how they can spread out in order to reach in 3 different directions. All right, so the way that we make a double bond is a sigma bond plus a pi bond. So in three-dimensional space, what a double bond looks like, and I'm just going to kind of partially do this. Here's my carbon and here's my oxygen. They're going to have a sigma bond in between, which has 2 electrons. And that is just the head-on overlap of the sp2 from the oxygen on the right and the sp2 from the carbon on the left. And then they're going to have a region of electrons above and below. And just like we turned an S into a sigma, we turn a P into a pi. So this is called a pi bond. Just like a p orbital, it comes from having electrons above and below whatever your axis is, and therefore the electrons that are populating the sigma bond are just smack dab in between the carbon and the oxygen, but the electrons that make the pi bond are above and below. Therefore, the sigma electrons and the pi electrons aren't really on top of each other, but they are always being shared between the same carbon and oxygen. So that's really, in three-dimensional space, what a double bond looks like. So let's actually do this and see how these guys kind of come together with the carbon that we just drew. All right, so I'm going to redraw my carbon down here, and I'm going to give it an sp2 coming off to the side. We're going to have a p orbital up and down. Right, so this is my p, this is my sp2. And then we still have these other sp2s, but we'll just put them in the back burner for a minute. All right, the oxygen is going to come in as something very similar because the oxygen would also be sp2. So if you look at that oxygen, it has 3 regions of electron density, 1 for a lone pair, a second for the second lone pair, and a third for that double bond there. So the oxygen, which we will draw over here, is going to also be sp2, and it will also form that same shape. And then it will also have a p orbital that is up and down. All right, so these 2 sp2s would get together to make a sigma bond, and these 2 p orbitals, which are parallel to each other, would get together to make a pi bond. In class, I'll show you how this looks kind of with models or with balloons so that you can really see them a little bit better in three-dimensional space. But what's happening is that the double bond, any double bond, is always made up of 1 sigma bond and 1 pi bond. And that is how we make double bonds. All right, there are also a couple other things to keep track of in this molecule. So formaldehyde has the double bond between the carbon and the oxygen, but what it also has is at the end of these 2 sp2s, we've got hydrogens. Right, so it's going to make a sigma bond right here and right here. And for that oxygen that's on the far right, what it has in its other sp2s is just simply lone pairs. And so that would be the full three-dimensional representation of this molecule. And indeed, when we do X-ray crystallography, we can see that the data supports the fact that these are the three-dimensional shapes that these molecules make. So once again, we can measure out what the bond angles are for an sp2 hybridized carbon or oxygen or whatever. And because these are just spread out as far as they can in really two-dimensional space, what we find is that all 3 of these angles, since they're completely flat, is just a circle divided by 3. So 360 divided by 3 is 120 degrees. So the bond angles for any carbon or oxygen or nitrogen that is hybridized sp2 would be 120 degrees. All right, lastly, let's look at hydrocyanic acid. Hydrocyanic acid is HCN. And it looks like this. So we can see that in hydrocyanic acid, the carbon only has 2 regions of electron density, and therefore, going through what we did before, it would take its 2s orbital and its 3 2p orbitals, and it only really needs to spread out 2 things because it's got only 2 regions where electrons need to be located. Therefore, we would only take our s and 1 of our p's, we would get something that's half S and half P. Therefore, we just call them SPs. These are 50% S and 50% P. Once again, they are shaped kind of like, I don't know, propellers with one big lobe and one little lobe. These are going to be much smaller than sp2 or sp3, and therefore they make even shorter bonds because they're half S, and the S is very close to the nucleus. All right, and once again, though, we would have two p orbitals that are unhybridized. All right, so if we kind of take our carbon here and we put one sp orbital off to the right with a big lobe, and one sp orbital off to the left with a big lobe. I know I switched those words around, but right and left, they're both there. Then what we would have are two sps, and what we would have left over is that we would have a p orbital up and down, and we would have a p orbital coming out at us and going back. The nitrogen on the far right would also have only two regions of electron density, so it would also be hybridized as sp. And so let's draw that nitrogen in. I will make the nitrogen pink for whatever reason. It would have an sp coming off to the right, an sp coming off to the left. Again, I mixed up those words. And then it would also have an unhybridized p up and down, and an unhybridized p out and back. And hopefully you get the idea of how we're going to make this triple bond. We are going to make a sigma bond in between using these two hybrid orbitals that are just going to share electrons directly in between the carbon and the nitrogen. We're going to make a pi bond that is above and below this nucleus by using those parallel p orbitals that are going up and down. So that's a pi bond. And then finally, and you might need to use your imagination in 3 dimensions, that p orbital that's coming out at us and going away for both carbon and nitrogen are going to form another pi bond in the front and the back. And so therefore, what we see is a triple bond, which is very hard to draw and very hard to imagine, I think, in 2-dimensional space because it's a 3-dimensional thing. A triple bond is one sigma bond and two pi bonds. Once again, a sigma bond tends to be made by either s orbitals in the case of a hydrogen or by hybrid orbitals. And the pi bonds are always made by side-by-side overlap of parallel p orbitals. So this is a sigma, and this is a pi. And you get two of those when you make a triple bond. All right. So let's talk a little bit about bond length. Bond length is just the distance between the two nuclei. So you can imagine that if you have something that is the distance between a hydrogen and a hydrogen, well, those are both s's. And so this is going to be extremely short because the orbitals that are overlapping are just s's. They're just little spheres. So this guy's going to be very short. All right, and the progressively larger orbitals make progressively larger bonds. Therefore, what would happen next is the orbital that's closest to an s is just an sp. It's half s. So an sp carbon attached to h of an s is also going to be very short. And kind of the distance is going to get longer and longer as we decrease the s character and increase the p character of all of these guys. So this becomes much longer, relatively. The same thing happens for double bonds and triple bonds. So a CC compared to a C double bond C compared to a triple bond C. Well, in a single bond, these tend to be sp3s. And the sp3 tend to be the longest because they're most like p orbitals. The sp2s tend to be smaller because they're more like s's. And the sps are even smaller. Furthermore, there are a lot more electrons holding these guys in together when you have a double bond or a triple bond. So relatively, the length of these guys, the carbon single bond carbon tends to be longer, and the carbon triple bond carbon tends to be shorter. So kind of if you're ranking all of these, we would just go 1, 2, 3, 4, 5, 6, 7. And that's relatively how long these molecules end up being. Oh, I forgot to mention this, but I can only imagine that it's fairly obvious. The bond angles for any sp or sp carbon or sp nitrogen are going to be just two things spread out as far as they can. So the interior bond angles for any of these are just going to be 180 degrees. So again, as a recap, if we have something that's sp3, the bond angles are 109.5 degrees. For something that is sp2, the bond angles are approximately 120 degrees. And for something that is hybridized sp, our bond angles are going to be 180 degrees. All right, thank you very much. I will see you in class.